Alright, so let's go through this squirrel review. I have a 3 kilogram flying squirrel and leaps off a cliff. How much does the squirrel weigh? Alright, so we want the weight. That's the force due to gravity. The way you think of it, that's going to be the mass times the acceleration due to gravity. So 3 kilograms times, I'm going to use 10 meters per second. You can use 9.8 if you want to, your call. I like the ease of getting 30 newtons. Alright, that's a 30 newton squirrel. Oh, I didn't name my squirrel. My squirrel's name is Jake. Jake the squirrel. Alright, so number 3. There are no air resistance. What would the squirrel's velocity be after falling freely for 10 seconds? Alright, that's my time. Falling freely means there's no air resistance. And I want to know the velocity. What will it be after? So that's the final velocity. Alright, so he jumps off. That initial velocity is 0. And it's falling, so I know my acceleration is, again, 10 meters per second. So if I have two velocities, an acceleration, a time, I want to find that final velocity. I just need to find the equation that has all of those things in it. And that's going to be the final velocity equal to the initial velocity plus acceleration times time. Alright, initial velocity is 0. Acceleration is 10 meters per second. Do that for 10 seconds. We get a final velocity of 100 meters per second. There we go. Alright, so how much distance does a squirrel fall in that time? Alright, so now I want a distance, a vertical distance, dy. And again, my acceleration is 10 meters per second. My initial velocity, again, is still 0. My final velocity is 100. Be careful just doing d equals vt because this is accelerating. You would need an average velocity, and you could do that, but I'm going to go with the equations that I have that tells me that the distance, sometimes in the equation sheet you'll see delta x as in displacement. Alright, this would actually be delta y, but it doesn't matter. Change in position. My displacement, my change in position, equals the initial velocity times time plus 1/2 at squared. And that'll take care of pretty much any scenario that you deal with motion. Vt plus 1/2 at squared. Alright, so let's plug in what we know. Initial velocity is 0. 0 times t, 0 times 10. That'll just go away. 1/2 times acceleration. Acceleration is 10. Time was 10 seconds. 10 squared. So the distance fallen is, again, 0 times 10 is 0. Plus 5. 10 squared is 100. 5 times 100. D equals 500 meters in 10 seconds. Also, you could have gone and said that d equals vt, right? But this needs to be an average velocity, right? That'll only work because we're accelerating if we use an average velocity. So on average, between 0 and 10 meters or 100 meters per second that it finished, all right, I take the average of those two numbers between 0 and 100, and that times 10 seconds, which would give me 50 meters per second on average, times 10 seconds. Distance again is 500 meters. Alright, so a different way to do it. I recommend this one because it works in every scenario. You don't have to worry about finding the average velocity. Alright, so let's look at number 5. We start dealing with forces. So the squirrel spreads the wings and now it encounters 20 newtons, so put my pencil back, 20 newtons of air resistance. What is the net force on the squirrel? Draw a free body diagram. Alright, there's my squirrel. I'll give him arms and legs, what the heck. Alright, and now two forces acting on this. We have the weight acting down, mg, and now we have air resistance. Alright, I'll call that F, air. Alright, we said this was 30 newtons. We said the air resistance was 20 newtons. So the net force is going to be the combination of these. Remember, they're acting in opposite directions. So we're going to have that weight, mg, minus the air resistance, because it's in the opposite direction. So 30 newtons minus 20 newtons gives me a net force of 10 newtons. Bingo. Alright, so using that net force for number 6, determine the acceleration of the squirrel. Alright, so acceleration and net force is one more piece of the puzzle we need, which is the mass there on the bottom. That's our second law. So, get the acceleration. Our net force we said was 10 newtons. It's from the previous problem. our mass, if you scrolled all the way back up to number 1, our mass was 3 kilograms. So right there, number 2. Alright, so 10 newtons over 3 kilograms gives me 3 1/3 or 3.3 repeating meters per second of acceleration at that moment. A little bit less than the acceleration due to gravity because of that air resistance. Alright, so let's look at number 7. Air resistance increases with velocity until the squirrel reaches terminal velocity. So describe the squirrel's acceleration and net force at terminal velocity. Notice this says describe. We're not actually calculating. We're describing it. So, I'm going to write in shorthand here. At terminal velocity, alright, that is when the forces balance. And what forces are we talking about? Well, that's when the weight, specifically pulling it down, is balanced by the air resistance. Air resistance, shorten that too. Alright, so if this were our object, force pulling down, force pulling up, same. So the forces equal out. So because the forces equal out, mg minus that air resistance is going to equal, well, 0, because they're equal. So there's no net force on this. Net force is equal to 0. Because there's no net force, because the net force is 0, the acceleration is going to be 0. No net force, no acceleration at terminal velocity. Alright, moving right along. Number 8. The squirrel lands on a branch. Branch applies a force on the squirrel, decelerating him or her. The squirrel also applies a force on the branch, causing it to bend. So if we look at that, we have this is our squirrel head, and this is the branch that they're landing on. And in blue here, I'll put the force of the squirrel on the branch, and then upwards on the squirrel is the force of the branch on the squirrel. That's the action force, reaction force that we're talking about. So, do those forces cancel out? Well, there's an action force and reaction force, right? So action, reaction. We know they're equal. We know they're opposite. But they're not going to cancel out. Why? Because they're acting on different objects. One is acting on the branch, one is acting on the squirrel. Alright, so they act on different objects. Because of that, they can't cancel out. Only if two forces are acting on the same object can they cancel out. Act on different objects. Alright, so that's the first half. We're going to move on. Alright, so our squirrel jumps off the branch with a horizontal velocity of 20 meters per second. How high is the branch? It takes 3 seconds to hit the ground. Alright, so we have a time here. How high is the branch? We have a vertical distance that we need, dy, and we have a horizontal velocity, vx, is 20 meters per second. Now we can't mix our horizontal and our vertical. So if we want the dy, vertical distance, we'll need to just use only the vertical information. So, again, with any motion, whoop, I gotta put on my pencil, I'm moving the paper here. With any motion, I go back to, so we have distance, I'm falling, so I'm accelerating. I also know the acceleration, 10 meters per second because I'm falling. So I have acceleration, I have velocity, I have distance, I have time. I need an equation that has those things in it. So, I go back to d equals vt plus 1/2 at squared. It's my old faithful here. That'll work for just about anything. Alright, so dy, I want vertical distance. Alright. The v here is the initial velocity. Now it has a horizontal velocity, but I need to not mix horizontal and vertical. So this is vertical only. Later on we'll do some horizontal stuff, but this is vertical only because I want a vertical distance. I can only use a vertical initial velocity. So it jumps off the branch with a horizontal velocity, but no vertical velocity, so 0. T is 3 seconds, alright, plus 1/2 the acceleration, still 10, and the time again is 3 seconds, that's squared, so again 0 times 3, 0, half of 10 is 5, times 3 squared is 9 seconds squared, so my vertical distance, 5 times 9, or 45 meters. That's the vertical distance. Again, this will work for any motion, just got to plug in the right stuff. Alright, so number 10. What is a squirrel's vertical velocity just before it hits the ground? So I want to know the final velocity just before it hits the ground. But I already have the time, I know the acceleration, and I know that the initial velocity was 0. All of this still vertical. So final velocity equals initial velocity plus acceleration times time. Starts at 0, acceleration of 10 meters per second. Do that for 3 seconds. Go from 0 to 10 to 20 to 30. So 30 meters per second is my final velocity once it hits the ground. And that's the vertical velocity. It still has that 20 going sideways. That's the vertical velocity at 30. Alright, number 11. Draw the path of the squirrel if it jumps off the tree with a horizontal velocity of 20 meters per second. How far away from the branch does the squirrel land? Alright, so if there's my branch, and I'm going to simplify the squirrel. There's my squirrel there. And it jumps. Alright, it's going to land a little ways away. So it's falling 45 meters. It's going to jump out. Probably not to scale, but that's okay. Alright, so I have a horizontal velocity, Vx, 20 meters per second. How far tells me a distance. How far away tells me horizontal distance. Alright, so it wants this distance. How far away? Dx. I already found dy in the last problem. How high? How far did it fall? That's dy, vertical. This is dx, how far away. So this is only horizontal stuff. And that's all I can use. I can't use any of the vertical information I had. I got to treat the two separately. Alright, but I'm going to go back to our old faithful. D equals vt plus 1/2 at squared. Alright. Now some of you might be already making a shortcut and say, Mr. J, you can use something simpler. I know, but I'll get there. Initial velocity starts off at 20 meters per second. Alright, time, 3 seconds. Plus 1/2 acceleration. Oh, 10. Wait, no. 10 is the vertical acceleration because of gravity. It's pulling it downward. It's not accelerating left to right. So that's going to be a 0 in there. So that whole term goes away. I'm left with d equals vt. The simple, the nice version. Nice and easy. So my horizontal distance here is 20 meters per second. Do that for 3 seconds. I've gone 60 meters. He lands 60 meters away from where he was before. Alright, d equals vt, because it's not accelerating left to right. It is accelerating vertically, but not left to right. Alright, so number 12. What's the horizontal velocity of the squirrel just before it lands? Alright, so again, started off at 20 meters per second. Acceleration in the x direction, horizontally, 0. Doesn't accelerate, so it doesn't change. So Vx is still 20 meters per second. Bingo. Alright, 13. What is the actual resultant velocity of the squirrel just before it lands? Now it's talking about resultants. So let's think about this. This squirrel, right before it lands, has a velocity of 20 meters per second this way, and a velocity of 30 meters per second downward, right? This is Vx, this is Vy. I did not draw that to scale at all, but please forgive me. Let's shorten this up a little bit. There we go. That's better. Alright, but I've already found my horizontal velocity, still 20. Vertical velocity I found up here, 30 meters per second. So at the same time, it's doing both of those. Alright, to find a resultant, I have 2 legs of the triangle. I just need that hypotenuse right there. So that final velocity squared is equal to, well, Vx squared plus Vy squared. I'm actually going to make those blue because I'm neurotic about color coding. Vx squared plus Vy squared. So that's 20 squared plus 30 squared. I'm going to pause while I get a calculator. 400 and 900. That's going to give me 1,300. And if you can do the square root of that in your head, I applaud you. Alright, got the calculator, and square root of 1,300 is Drum roll, please. I turn on the pencil. 36.05 meters per second is its actual velocity as it's hitting the ground on the angle that it is. Now remember, we can combine these. I could do this like because I have two velocities, right? Don't start to mix distances and velocities in this Pythagorean theorem here and how you approach this. All right, moving on to number 14. The squirrel decelerated when it hit the ground from that velocity. And number 13, to rest in 0.1 seconds. What was the squirrel's acceleration? Alright, so we want to know, oops, turn on a pencil here. We want to know the acceleration. That's the change in velocity over the change in time, if you look at your MCAS formula sheet, which is really just a rearrangement of the equation that we developed before. Final initial velocity plus acceleration times time. If you rearrange this for acceleration, you get that. Change in velocity over time. So, let's move down here and let's look at the velocity we had before. So, if the final velocity, right, was 36.05, and that goes from that to, I'm sorry, I guess we're stopping. We should call that the initial velocity in this case, because our final velocity is, well, 0. It's hitting the ground, stopping. So it starts at 36.05 to us, and then hits the ground in 0.1 seconds. So that's our time. Alright, so acceleration is change in velocity, final, which is 0, minus 36.05, which it had while it was right before it landed. That all happens in 0.1 seconds. Oops, not point t, 0.1 seconds. So the acceleration is negative 36.05 divided by 0.1, and that gives me negative 360.5 meters per second of acceleration, and it's negative because it's slowing down. It's in the opposite direction of the direction that it's going. Alright, so how much force is needed to cause the deceleration at number 14? So how much force is the ground pushing up on our squirrel here? Well, let's see. If we want force and we're dealing with acceleration or deceleration, force and acceleration, well, that has to do with mass as well. Alright, so we want the force, so we're going to rearrange this to F equals ma, which is actually what shows up on your formula sheet. The mass was 3 kilograms, if I do remember correctly. Acceleration is negative 360.5 meters per second. And let's see, pull up the calculator. 360.5 times 3 gives me a force of 1,081.5 newtons. That's how much force was applied by the ground onto the squirrel in order to stop the squirrel's motion in 0.1 seconds, which is pretty quick. Alright, so we take a drastic turn to number 16 and move on to gravitation and a little bit of circular motion. So Jake, our flying squirrel here, leader of his or her squadron squirrel brethren, is actually an alien visitor from a distant planet known as Lawrencetown. We'll go with that. It has 1/3 the mass of Earth and 1/4 the diameter. How much does he or she weigh on his or her home planet? Alright, so the old force and its old weight was 30 newtons. That's good to know. We want to figure out the new weight. Alright, so we ask ourselves, how did it change? Alright, how did the force change? To figure out how the force changed, we got to figure out, well, how the mass changed and how did the distance change. The relationship that pulls these together, Newton's universal law of gravitation, everything pulls on everything else, directly proportional to the masses, inversely proportional to the square of the distance. Alright, directly, inversely proportional to the square of the distance. This will take care of it all at once. So whatever changes, we can plug in however that changes in there, and it'll tell us how the force will change. Alright, so let me plug in. It was 1/3 the mass. Alright, I'll plug that in. And let's assume that the squirrel's mass doesn't change. I'll keep that as 1. Only one of them is changing. And the distance, though, is 1/4 of the distance, and that's squared. Alright, I'm just plugging in how things changed to this relationship right here. So I have 1/3 on the top, and 1/4 squared. 1/4 times 1/4 is going to give me 1/16. Because 1/4 times 1/4, I multiply the numerators, I multiply the denominators, I get 1/16. Alright, so I have a third divided by a 16th. Now that's kind of awkward. Now you could just divide them out and get decimals. Look at it as 0.3 repeating divided by, let's see, what's 1/16? 0.0625. You could do that. I tend to like to rearrange it. I'm going to zoom in here a little bit. So instead, I tend to do this. I look at it as 1/3, that numerator. Instead of dividing by a fraction, I'm going to multiply by its reciprocal. So dividing by 1/16 is like multiplying by 16. Alright, so that gives me 16/3. Or, what's 16/3? 16 divided by 3, 5 1/3. Alright, so it's 5.3 repeating times what it was. And if we divide this out as well, we'll also get 5.3. So, whichever way makes sense to you. If you like to convert it to decimals, divide them out, go for it. If you're comfortable rearranging the fraction here, go for it. Whatever you do, you're going to come up with that. But remember, that's not our weight. That was how the weight changes. So the force is now 5.3 times as much on that old home planet than it is on Earth. Alright, so if I can move this stuff again. Alright, we want to know what that new force is. Well, let's see, the new force equals the old force times how it's going to change. So times 5.3 repeating. So 5 1/3 times the old force was 30 equals 30 times 5 repeating equals 160 newtons. That would be the new force on that other planet. And pretty much every gravitation problem is the same. How did things change? Plug in how they changed into our relationship here, and the question's either asking how it changed or it's asking for a new force because it gave you the old force. Alright, last but not least, why does every object turn in a circle? Well, in order for anything to orbit in a circle, if this is our object, a couple things need to happen. You need a force pointing toward the middle, even if it's turning, even if you're looking at only half of that. You need a force turning in the middle. Let's say it's a car, not even going in a circle, but it's just making a left-hand turn. The force still needs to be turning inward, or pulling inward. The velocity, though, is going to be tangent to that circle. The velocity is tangent, always straight forward. So if it's moving in this direction, it's going to have a velocity in that direction, always straight forward, tangent to the circle. The acceleration, though, is always in the same direction as the force. The force causes that acceleration, so the acceleration is in the same direction. So, why does any object orbit or travel in a circle? It's because of that centripetal force pulling inward. That centrifugal force is really just your own inertia, a feeling of being pulled outward, even though you're not. Alright, that's it.